Okay, so parallel lines, they're sad because they go their whole lives, or non-concurrent lines, we call them normally parallel lines, but non-concurrent lines, they go their whole lives and they never meet. Very sad. Concurrent lines, or non-parallel lines, they meet and then they spend their whole lives drifting apart. Really, just the mathematics of lines is quite sad. Anyway, in this case here, do these meet anywhere? Anywhere in space? If I extend them out forever, their whole lives, have these forces ever cross paths? Did they ever meet? Yeah, they did. They met here. So, back in the day, I used to always label this with OMG, PMC, POC. Point of concurrency. That's the point where they're concurrent. If they're concurrent there, that means this force also is concurrent there. So it's going to be that angle. If you know that, that can speed up. If you know that, that can speed up your equations. Right? You can then get the protractor out, and then boom, bam, boom, you've solved the question. I mean, unless you're one of those people who doesn't own a protractor or can't figure things out. Look, a little bit of math sass there for you. Okay, so the point is concurrent and versus non-concurrent lines. Okay, how many minutes that took? 5 minutes to go through those. Okay, now we need to talk about resultants and equilibriums. I talked a little bit about this at the start. Remember, like alias, we started at that point and then we worked up to it. Okay. I have three forces. This one here is horizontal, and it's 6. This one here is at 45 degrees, and it's 7. And this one here is at 60 degrees, and it is 8 newtons. We're going to make all of these forces newtons. We're going to replace these 3 ropes. We're going to be like spies. We're going to go in there and we need to steal those ropes. We need to keep things so they don't catch us. So we're going to replace the ropes with one rope. What rope are we going to replace it with? Well, because I did this just recently, I think it's probably going to be about, 70 degrees up and 13.9 or something. But we'll see. We'll see how strong does this rope need to be. Okay, so first of all, what we're going to do is, because I own a protractor, I'm just going to draw this diagram. I'm going to draw this as, oh yeah, that's about 6. And then we make this about a little bit bigger, 7, and then that'll do. So let's do, I drew here 6, then 7 at 45 degrees, and then 8 at 60 degrees. How far am I from the start to the finish? This is going to be what we call the resultant. Now, I always draw a resultant I always draw as a dashed line, like that. Yep. Now, how far is that? If I got my ruler out, because I own a protractor and a ruler, if I got my ruler out, I would measure this and I'd say, oh, it's about 14 newtons. And you know what? A maths teacher would say, it's not 14 newtons. That's inaccurate. But an engineer would say, especially an engineer who's marking the HSC, would say, no, that's fine. Because remember, we use 10 for gravity, right? So we know that our gravity is out by 2%. So you can imagine that we're going to be pretty flexible when it comes to graphical solutions. I can tell you again that I saw that only less than 3 or 4% of students actually use graphical methods. And I can tell you that markers are super lenient. We will go out of our way to say this student has made a legitimate attempt, right? They have drawn a graphical solution. Let's find a way to give this student marks, even if it's not 100% accurate. Yeah? Okay, so that is a very common mentality, right? So what we can do is we can measure it, but let's assume that you don't like that method. Let's say instead, and I'm going to use a whole nother color again now, what we're going to do is we're going to break this up into its components. We're going to say 7, we don't like no 7s, we want to see horizontal and vertical forces. What is the horizontal component of 7 at 45 degrees? Anyone? Okay, well, I happen to know what sine 45 is. So if I said that this is 7 sine 45, which is the same as 7 brackets 707, which, if you guys type that into a calculator, please, I believe it's going to be something like 4.9.
Yep, 4.94.
4.9 will do for me. Okay, what's the up? It's going to be the same, isn't it? Because that's how isosceles triangles work, right? 4.9 up. Okay, so I've got this 8. I don't like diagonals, and you know what? My friend Excel, he doesn't like them either. So what am I going to do instead? I'm going to say that that one there is going to be, is that adjacent or opposite to my angle? Well, okay, here's the funny thing. I didn't say this in my last recording. My angle is here, which means alternate angles, it's also going to be there. So in this case here, if this is 8, I'm going to put the 8 on the inside just to make things a bit easier. If this is 8, is this opposite or adjacent?
Opposite.
Opposite. So I guess I'd write that as like 8 sine 60, right? But I'm going to write that down as 8 0.866, which is going to equal, I don't know, a number. This one here is going to be 8 cos 60, right, because it's adjacent, right, which is going to be 8 times 0.5, and that one here is going to be 4. Can anyone tell me what this one is? Is it 6.9?
Yeah.
Good work, thank you for that.
Yeah.
Okay, so then the question is, how big is, what I want to do is I want to complete the triangle. Yeah, I want to complete the triangle. So I know it's going to be going up and I know it's going to be going across, but how tall is this side of the rectangle? See how it now makes a rectangle? I've made a rectangle all around it. How tall is the rectangle?
6.9.
Plus 6.9 plus 4.9 is 11.8. Okay, and then how wide is the triangle? Well, okay, so how wide is the rectangle? The rectangle is 6 plus 4.9 equals 10.9. Okay, and then this one here is 10.9 minus 4 equals 6.9, yeah? Is that, are we good with that? So let's draw that over here. Our resultant is going to be 6.9 versus 11.8. We good with that? Now, how am I going to solve this, Max? Nope. Pythagoras. I'm going to do 6.9 squared plus 11.8 squared, and then I'm going to take the square root of all of that. What's that going to be? Jack, you on it?
Yeah.
Good man. I was going to write down 189 for a second, and then I thought, that would be absurd. And I forgot to square root it. Right? The point is, I used estimation to save me from an embarrassing error on camera. And my answer equals 13.7, yeah, close enough. Okay. Now, what is this angle? We like to draw the angle from the horizontal. Right? So this angle here equals theta. But that's the same as this angle here. Yeah, because vertically opposite angles, alternate angles on parallel lines are equal. Okay, so I'm going to use what function? Alex? What function do I use to find angles? It starts with a t, or it has a t in it. Okay, but it's not quite tan, it's something else. Arctan or inverse tan. So let's write that in. Okay, so we're going to say that the angle theta is equal tan to the negative 1. Opposite Remember we're using opposite of this side, is 11.8. It's taller than it's wide, yeah? It's taller than it's wide, so that means we're going to need a high number, right? Versus 6.9. I put that in here, I type in inverse tan, 11.8 divided by 6.9 equals 59.6. We're going to call that 60 degrees, that's close enough. Yeah. Okay. That's a resultant. Now, this is confusing. This is confusing. There is, back in this situation here, there's a force that's preventing these three cables from flying away. That force that's missing, the force that's needed to create balance in the force, or equilibrium, is called, unsurprisingly, an equilibriant. And that equilibriant is equal and opposite to the resultant. So the equilibrium is exactly the same number, but in the opposite direction. And I show that as a solid line. Realistically, for most of the examples we're going to talk about, we very rarely care about resultants. Very rarely in Year 12 do we care about resultants. We typically care about equilibriums. We want to make sure that everything is in equilibrium. My thing is that as a civil engineer, if it's moving, it's broken, right? So it's never moving. There's always an equilibrium that's holding that back, the three cables. Yeah, there's always something that's keeping this thing in equilibrium. But sometimes, in the case of like the girl who was lost in the woods, we had a resultant. Okay, so that's the difference between equilibriums and resultants. It is covered, I don't remember what page, I think the late page is 54 or something like that, they talk about that. Okay, thanks very much guys.